IC design.
Telecommunications.
Also telecommunications person. Okay. We're live? Okay. So I think we can get started. So thank you for those who are present and those who are following us online. My name is Ammar Kouki. I'm the founding director with the LTCC-Enabled lab. And I'm part of École de Technologie Supérieure, abbreviated ETS, based in Montreal, Canada. And today's talk is LTCC-Enabled RF components and subsystems for 5G and beyond radio communications. So before I get started, I want to say one slide about where we are. So this is downtown Montreal. What you see in yellow is our campus. We are the second largest engineering group in Canada, the University of Montreal in Ontario. Graduate 1 of every 4 engineers. And we have a very good placement. And we work a lot with industry. That's the key to our success, I guess. We work extensively with industry. So with that out of the way, I would like to thank TÜBİTAK. I'm here thanks to TÜBİTAK because TÜBİTAK has this program for people on sabbatical like myself. And I'm here working with Professor Hossein Arslan at the DIPOL. Some of you know is leading researcher in 6G and 5G communication. And also collaborating with Professor Aktuman at ETU, working on a separate subject altogether, microwave imaging of breast cancer. The intersection is always microwaves and electromagnetics, virtual model stuff. Okay. And I also would like to acknowledge my team. I'll present results, but I don't do much of the work. It's really mainly my students, which is currently one postdoc, PhDs and masters, and a couple of technicians who actually run the lab. Okay, I also like to thank our partner, Vibrance. So I'll talk about LTCC. They provide us the materials. It's a costly technology, but we are lucky that they collaborate with us and they support us with materials for prototyping. And these guys provide the money. You need it's a recipe. You need ingredients, you need students, you need materials and equipment and so on, and you need money to run this. And these are some of the companies and the funding agencies that fund our research. So with the acknowledgements out of the way, today's talk, I'll start with an overview of LTCC technology, and then I will go into what you can do with it, the research types, the kinds of things you can do with it, and focus mostly on the stuff that's relevant for radio communication. And I'll cover some of these. Depending on time and how much, how well we're doing, I'll cover things. I might skip some things. And then at the end, I'm very short. So the starting point is this low temperature coal-fired ceramics. What is low temperature coal-fired ceramics? The word low temperature is actually referencing to the temperature at which the ceramics are sintered. Ceramics is like the regular ceramics, you have to cook them in an oven. It's called low temperature because we have to sinter at 850. The reason we do that is because if we go higher than the silver and gold, which are the conductors, use that. So that's the low temperature. Coal-fired, it's because we actually make multi-layers and then we fire them together. So it's like making tons of circuits. Each layer is its own circuit. Sample them together, you fire them, you sinter them together. That's the coal-fired part. Okay? And ceramics, obviously, because the underlying material is ceramics. So why ceramics? Well, ceramics are very good because they are low loss material. And 5G, 6G, energy performance, energy efficiency is critical. RF losses low conductor loss. Particularly if you use silver, you're using the best conductor. It's the lowest. Okay? And it's actually very suitable for high frequency. So some of the materials, classical materials, not good for applications. The loss tangent becomes too high. So, and they're actually very nice, temperature stable. So it's a nice technology, and it's very useful. And we'll see that it also has some other advantages that we'll discover as we go on. So what is the process of making circuits in LTCC? Okay. So we start with what is called green tape. So this is ceramics that's soft. Okay. And then the first step, we do the blanking, so that we cut them to the size that we want. You do vias, where you're going to have interconnects. You fill the vias with conductor, silver, for example. Then you print the patterns. Each layer gets processed on its own. Then you stack them together. We press them into a high press, cut them, then we fire them, then we can do post-treatment. So this is it's a chain. So typically, this kind of chain is hard to have in university lab, but we are lucky that we have a full chain, full process. So these are the steps, okay? And you need the machinery to do this. And in terms of the materials, the main materials we work with, we have two types of materials. We have a low performance, low cost material, L8, okay? And the high performance, low loss material, called A6. We also have some other experimental materials in the lab that we have through vibrance, okay, with higher dielectric constant. So if you look at this material, it's actually a dielectric constant of around 6. It's a loss tangent below, 10 to the minus 2, 2 10 to the minus 3, up to close to 100 gigahertz. So this is very low cost material. Okay. And as a matter of fact, vibrance has some new experimental materials that are even as good or better with higher dielectric constant. Okay. And higher dielectric constant for a dielectric design, as you know, it shrinks the size of circuits. So low loss, good dielectric constant, good stability. So these are all good things. So these are some of the metallization. So we can use silver, gold, and we can actually mix silver and gold. Silver is not good to be made at the surface because it oxidates over time. Okay. Gold is very stable in that regard, but if you do silver inside, you're getting the best conductance of the lowest loss. So, and if you want to hybridize, you want to mix, then you have to have these special materials. So why are these? Why a quick detail? We work with pastes because we do printing. Instead that we print, okay? So it has to be a paste, and these pastes, when they are fired, they have the conductor and they have some other chemicals that will evaporate during the sintering process. Okay? So these are specially engineered materials, and that's what vibrance or ferro provide for us. So how do we do this? I said it's a process, it's a whole chain. Okay? And this is my lab. Yes. So you can see here we have the whole chain. Okay? Each machine is actually performs one of the steps. Okay. So what's the characteristic of this machine? This is a class 10,000. It's a relatively clean room. So we don't have particles that are. So if we do feature size down to a few, couple of mils for microwave engineer, but 150 microns type of solution, we need a clean environment to handle this. Okay. So we have, so this is the list of materials that we use, and this is actually, it's industry grade. Okay. So this is actually, it's a university lab, but we can do small volume production. It's semi-automated. The technician, this is our printing station. We have to print, we can print many sheets, and take those sheets and take them to the next machine, and stack them. So we can handle small volume. It's not fully automated. And we have lots of collaborations. We use it in our group, but we also have companies, other universities, and so on. And today, I would like to, for designers, if you guys are interested, for them collaborate. We have mechanisms, we have design rules, we have documentation. So if you want to use this prototype, some testing, your model. So, what is the potential then of this technology? Imagine you have this stuff, you have this technology, you have this fabrication, clean room, you have the test equipment. I didn't mention you have test equipment we go to 67 gigahertz in the lab, and within Montreal we have a consortium where we can go much higher in frequency. So what can you do with this technology? So the number one thing is, obviously, this is high integration density. You can just condense stuff, you can integrate stuff. Okay. It allows you to do size and weight and power reduction, swap factor. It's very good for swap. Obviously, low loss. So you can now make low loss transmission lines, loss guiding structures, low loss interconnects. It helps with that. It can do hybrid waveguide transmission line lumped elements. So you can do capacitors and inductors that are lumped elements, but you can also do transmission lines. You can even do substrate integrated waveguides. So it's quite versatile. And you can also even go all the way to antenna integration, and you can do functional substrates. The idea is, if you imagine you make a stack like this, or part of this stack, this part becomes your substrate on which you can do other things. That's a functional substrate. So that's something I'll show you that we have done, and I'll show you fluidic application. It's like I mentioned, it's good for temperature harsh environments, high temperature. It's good up to 100 gigahertz and beyond. Okay? You can do system in package, so it's actually quite a nice technology to have. Okay? And we are lucky to have this technology. So then what can you do with it? So this is actually a snapshot of this lab. I created this lab around 2008, and it became fully functional maybe a couple of years later by the time we got all the equipment in. And this is what we are doing today. Okay. And today I'll try to cover some of these things, not everything. But let me talk about the vertical. So one axis is for field programmable RF frontends. Okay. This is essentially a game changer for wireless. Hopefully, I'll convince you why this is great. Field programmable RF frontends, and there are different topics. If you try to do this, and this is not an exhaustive thing. It's just some of the challenges you need to address. If you want to do field programmable frontends, you need a lot of building blocks. Okay. I'll spend some time on this. Power and efficiency, power amplifiers. The Achilles heel of communications and efficiency is power amplifiers. Because, I guess you all know, if we want good communication, we need high peak to average signals, OFDM type stuff, and so on. And these guys, PAs, they hate those signals. They become very nonlinear and very inefficient, right? And that is really the billion-dollar question. How do we get this system fixed? Okay? I don't claim to have fixed anything, but we're doing something like everybody else, trying to find solutions. Okay? From whether it's a circuit-based or architecture or distortion or down to recycling of power, thermal recycling. So trying to look at ways to improve power amplifier efficiency. So for low loss and size reduction, size and loss reduction, we've done some stuff for how do we actually make airwave guides? Because we know airwave guides are lowest loss guides that we can use if we can leverage it. So it looks like we can do some of these. Can we do stuff instead of going horizontal? Can we do vertical? So that's something we do. Can we do suspended lines instead of printed lines? So on. Okay. And can we use higher K materials, higher dielectric materials? And this is something we're trying to explore. If you go in the way to system 3D and integration, then you can do stuff for interposers. So if you're trying to make multi-chip and you want to connect them, you can do ceramic interposers and suffer and deal with all of that. We try to develop some ceramic interposers. We've done some work with high-speed optoelectronic integration using LTCC. we've done some advanced duplex instruction. So for full duplex, big problem is isolation between transmitter and receiver. So the transmitter talks loud, the receiver listens to those signals, how to duplex and have high isolation. And as a matter of fact, we have a patented technology that we licensed to a company and then using in a commercial product. Then we can do directional filters, we can do lumped filters, and we have done some integration of antennas, ceramic antennas, dielectric resonator antennas. So for the rest of the talk, so forgive me if I go quickly over things, because I just want to give you a flavor of what's doable. Okay. Obviously, if there are questions, whether it's today or later, reach out and ask. Okay. So the spectrum. Okay. So I love to start here because what happens is we start doing stuff as engineers and we got carried away. And we rarely get the chance to actually look back and say, what the heck are we doing? So this is the spectrum in 1945, okay? And this is reproduced from the British Institution of Radio Engineers. And it says, it amply evidences the saturated state of international frequency. This, my friends, is a saturated spectrum, if you believe it or not, to the guys in 1945. And what did they want to say? So this is and they say that the progressive, okay, it also indicates that progressive radio and electronic development is bound to necessitate what? Necessitate infiltration into higher bands. Sounds familiar? Right? Yeah. And we have to go into other areas of frequency. So this is 1945. How is that spectrum today? This is the Canadian allocation. This is, okay, you're looking at UHF, SHF, 3 gigahertz to, so there's 300 megahertz to 3 gig. There's nothing left. Okay? So this is basically, we're on a galaxy spectrum. Okay? So this is the spectrum crunch. We're in this context. Right? Yet, our friends in communication, what do they want? What did they do, actually? They started with this MTS stuff, few megahertz max, moved to 1G. First time we have these amps, analog systems, then 2G, when we start to introduce the GSM and the digital stuff, 3G, so every generation builds on top of the other, needs more frequencies, okay? 4G LTE, we are up to 26 and 700, okay, 5G, and you see what's going on, okay? 6G, people want to talk about terahertz. This is what's happening. And you see, today we have the problem. 1945, they said we have a saturated spectrum, but we continue to increase demand for spectrum. It's continuously increasing. So if you look at that picture, okay, you look at this picture, what's going on? When the spectrum allocation and usage is actually discrete, it's fragmented, it's rigid, fixed. Okay? And why is that? Why? Well, my argument is that this has to do with the hardware. Okay? There's legacy, obviously, and you do things because you're able to do them a certain way. We started in 1945, we moved, okay, and every time we did things because we do spectrum management, spectrum allocation, because we're building on legacy. Because the technology we had allowed us to think that way. So for me, if I look at the hardware, I say the digital in baseband, it's really no longer a limitation. Back when, early on, we had a dedicated chip, it will do one modulation. You want a new modulation, get a new chip. Today it's SDR. Today, you could do OFDM on one frame, the next time you can do something else. So digital is done. We fixed that problem. So what's left? It's left this RF stuff. The RF stuff, and you all know this, right? This is the 3G mobile terminal a few years ago. The G's have been coming fast and furious all the time, right? So, a few years ago, you open a 3G mobile terminal, and welcome to misuse of resources. Everything redundancy. This for that, this filter for that, this amplifier, this. It's all, okay? There's a lot of hardware redundancy, and this is not good for sustainability. It's not a good way to do things. Okay? But because we have to accumulate all of these legacy bands and frequencies and so on, right? What happened with 4G? Didn't get better. It actually got worse. Okay? And so today, in 5G, this is the Samsung Galaxy S21 front end. If you look at it, okay, it has a bunch of modules. It looks that it's less cumbersome than 4G, but it's actually much tougher to make, and it's much costlier. Now, today, in the RF front end is the biggest cost driver of these terminals. Okay. Although it looks like, because all of these chips now, they have to do a lot of functionality. It's not that we do less, it's just the chips are integrated. RFIC designers have to do magic. Okay. You have to really do magic, and this becomes very tough. You want to accommodate lots of standards, lots of frequencies. That's it. Okay. So my proposition to you is that this is not the way to do it. And to drive this home, this context. Okay. So I will contrast the filter. Take a filter, okay? If you are an FPGA or you want to do it in FPGA, in a digital, in the baseband, okay? This is all you have to do to write a filter. It's actually software. You can take a high school kid, teach them programming, that's it. So baseband stuff is democratized. It's accessible. It's easy. Okay. Now, how do you do an RF filter? Okay. So the RF designers say, okay, number one, am I going to lumped element? Is this a high impedance or impedance, blah blah blah, distributed, the resonators, lumped elements, waveguide? It's a jungle. It's not trivial, right? You essentially, it's not democratizable. You need this misjudged brain. You need to have this, this knowledge. So this is actually, it's not good. It's not a good starting point. We have to do something about this gap. There's a huge gap, the digital and the RF. And why is this, and what can be done about this? So this is actually the context why I'm trying to work on field program. It's essentially a way to try to finish this development. Okay? And in the process, hopefully, the process is we want to go from this is kind of the dream in a way. Okay? To summarize this dream, this is what I want to do. We want to go from that front end to a much simpler front end. That's field programmable. And by field programmable, I mean something that would look something like this. You have the baseband saying, okay, I want this channel, I want this bandwidth, I want this gain, I want this front end performance. And that's all you need. And then you go and it programs itself. The next time or the next time frame or whatever you want to do, it becomes like this. So this should use a lot less resources, provide a lot of agility, and this will allow us, hopefully, to need less spectrum, less resources, and less of everything. So if we are able to do this, well, we will close that gap. We will have this, programmability. So this is really what we're after, as in the long shot. This is the big outlining frame of the research. So we have a few designers that might recognize this. How do we do this today? How do we do actually? We don't have that field programmable. But when we develop a front end, how do we do it? As a matter of fact, if you take the case of an amplifier, your device is here, you probably have some model for the device. And you have to design this. You have biasing circuitry, that's figured, no problem. Okay. So really the biggest issue is as you change here, you need to tune this matching network, input and output, to get your desired performance. And then you can sweep the load and you can do all these things and you use the Smith chart a lot and all of these things. And hopefully at the end you say, okay, I'm getting some gain performance, some efficiency, and that stuff, and it's optimal, let's go make it. That's really what we do, right? How do you make this program? How do you make this process program? Okay. So if you're actually, in the software, let me go back. In the software context, this is, I'm tuning this. The simulation engine, when I have ports here, is actually making measurement, the pseudo measurement. Simulation, if I have an actual device, and this guy is tuning a filter, for those of you who know how this works, when you do this waveguide filters, we have screws. No matter how good your design is, you have to sit in front of the network analyzer, tweak this bit. So basically, you're doing tuning, like you're doing tuning of the matching network, and measuring. Okay. So field programmability, reconfigurability of tuning, and integrated and measurement will give you field programmability. So this is really the idea that we want to do. We want to see how do we do this. Okay. So what I've been working in, and I have a patent of this, is what I call in-hardware design or design as a way to program. In other words, we need some components, diodes, MEMS, or microfluidics. We'll mainly focus on these to provide the reconfigurability. And we need integrated measurements. We need to measure. We have to bring the equivalent of a network analyzer in the circuit. Nothing less challenging than that. Okay, that's what we need. Okay. So this is recapitulating the idea. If we want to do the in hardware design, we'll have a device. We can vary the biasing. We need the variable input matching, variable output matching, and we need measuring. That's what these are the building blocks. Okay. This is essentially the same thing, but you can say here that we have a controller that's controlling biasing circuitry, the vector network measurement, and the input and output tuner, tuning the impedance. So how do we do impedance tuning? So we have two ways of been working on. We can work on doing with fluidics or with MEMS in LTCC. If you do with fluidics, the idea is very simple. We say that if we have a transmission line, a sectional transmission line, if it's in pure dielectric, it has one impedance. If I put a fluid on it, it changes simply. That's it. Okay. And if I make a cell like this and inject the fluid, when the signal passes, when the fluid is there, it is an impedance. When the fluid is not there, it's an impedance. And if we make enough cells of those, okay, so here is a cell that prototyped and measured. We made a cell, coplanar line with a cavity on top of it in LTCC, what I explained, that layer is right. We put a cavity, and we pump liquid in and out. When we pump the liquid, if it is air-filled, we have a 50 ohm line. When it's not air-filled, it moves. And that's really the basic concept. We need a unit cell like this, and then if we have that unit cell, we can make multiple cells. So if we have multiple cells, I have 8. In essence, I have 256 states. Each one is 2 states, it's filled or empty. Then what is happening? As I play with these states, I'm able to generate many impedances in the Smith chart. So ideally, you want to cover the whole Smith chart. But it's not a problem if you don't cover the Smith chart. Because if I look at this point, for example, this will give me infinite matches. But if I put this point and the impedance I need is here, it's probably giving me 20, 30 dB match, which is practically good enough for work. So that's what So this is actually a simulation and measure. And the important is not that the points fall exactly on each other, it's that they have this coverage. And this stuff turns out to be very good for low frequency. Sub-6, when you go to low frequency. And the fluidics are very good. They give us coverage and they have good power handling. Lots of power, no problem. Okay. And so this is an example. We take a transistor, we put an input matching. It doesn't need much output, so we integrate. So this is an LTCC. It's a multi-layer. These are the cavities. Biasing the device. And then when we tune this, we tune in this amplifier. This amplifier is, I can actually tune it over, and in its case, what I'm getting close to the maximum stable gain that I can achieve. So instead of doing wideband design and trying to compromises, I can actually design for the frequency that I need. If we want to do this with MEMS, okay, so this is our first try at this. We developed a MEMS, so this is a slow wave structure, a CPW slow wave structure, and they're connecting different cells, and here we have a capacitive MEMS switch. So it's a two parallel plates, you apply voltage, you get closer, you have higher capacitance, higher, lower capacitance, just change the capacitance. Okay? So this is the an SEM picture of the fabricated device. Okay? And this is an actual photograph of the tuner. It has 8 cells, these are capacitors, okay? And it measures 4.2 millimeters. So, and this is the kind of impedance is able to generate at 5 gigahertz. If we take this now, so this is a gas and match transistor. Okay, so we took this device, we wire bonded it to these tuners, put the tuner in and out, and program this program on that file. So if we have these switches 1, 2, 3, 4, 5, 8, so 1, 2, 3, 4 on, I'm at around 3.7. 3, 4, 5, 6, I move to 4, 1. And then you can see. Again, in each case, the gain is close to the maximum stable gain. So I'm able to achieve kind of an optimal design. Obviously, these are gain stages. It's not a PA per se, but you have to start somewhere. This is so the concept now, okay, validate. But this obviously this is a conventional MEMS process. MEMS on silicon. It's not using LTCC. How do we do this in LTCC? So actually we are able to do this, and I'm not going to go into a lot of details, but basically the LTCC is not good for MEMS because when you fire the end product, it's actually quite tough. So we need to do a polishing step. Once it's polished, then we do a traditional MEMS, position lithography, and so on, and make MEMS devices. Why do you want to do this in LTCC? Remember what I said that this substrate could be functional substrate. I could have a lot of circuitry. I could do power amplifiers, filters, whatever, lectures, products. At the end, I need the surface to polish it, so I shouldn't have any devices on top. Then I do a lithography on it. And then I do like a single layer process. I put MEMS devices, semiconductor devices, I can printed lines, okay, but using lithography. And that's the idea of the process that we have put together. And this is the second clean room where we do this. So we have 2 clean rooms adjacent, one to the other. Okay? The first clean room we do LTCC. The second one we do this MEMS process. Okay? It's a class 1000 yellow room. Okay? So that where we do this processing. This is actually a snapshot of the process, how it works. So we do the standard LTCC process that I mentioned. Okay? A lot of circuitry at the end. You need vias to the surface. Whatever needs access to the surface has vias. Then that gets polished after sintering. And then we do a MEMS process. So this is an example. For example, if we look at the MEMS switch, this is my RFA. And I have bias, my bias circuitry is buried. And this is immense capacity switch that we've designed. And these are two versions. So again, it's a two-state. When it's in the up state, I have 50 ohm. In the down state, my impedance is changing. That's version 1 of the design. This is version 2, the second design. Okay. And this one we designed to handle a bit more power. So this is capable of handling about 2 watts of power. Okay. And you can see this is the measured and the probe testing, and this is this is the animation of what's going on in there. And the performance of this switch is actually, it has an activation voltage of close to 30 volts. And remember, 30 volts, but little or no current. So this is not, it's not a lossy component. Really can have very, very low power consumption. And this is, by the way, I actually do have some samples of the stuff here. If you want to look at them after the presentation, some of these ceramic things, including these tuners, these impedance tuners, and you see the kind of coverage that we have with it. So if you look, for example, this tuner, although we're generating these points, but in terms of gamma, anywhere I can achieve better than 10 dB large, all the way to the edge. And that 12 gigahertz synergy. So, okay, so this is what that single capacitance switch used in a tuner. So this is, we can dispose them linearly, or we can try to make them more complex. So this is what we're doing with this technology. So this is again showing you the kind of performance. As a matter of fact, when we go to 7 gigahertz with this latest design, we have a lot more coverage. All right, so I hope that you're convinced that we have a path for doing this piece. Okay. Remember now, to get the whole thing working, remember I'm tuning this. So this is my MEMS devices. They're doing input and output, but the question remains: how do I know that I have the right design? When I have the network analyzer, it's good. But now imagine that this is field programmable. You have a device, you want to program it. How do you know? Okay. And the issue is, for the RF designers, you know that there's a lot of drift, that things can change, and so on and so forth. So, as a matter of fact, we don't want to care. We don't want to work with hardware. We want to work with the actual hardware. So, what we need is a way to measure embedded. Okay. So, this is the embedded measurement solution. Okay. And this is essentially, we're saying, for the RF expert, the relatively instantaneous, we're actually going to use a 4-port interferometer. Okay. And the idea is we want to sniff signals. Okay. We want to use non-directional sniffers to sniff a little bit of signal. We sniff the forward and backward values together. Okay. But we know that this is a passive structure, and we know it's S parameter. We know how it exactly how it sniffs. That information is known for us. And so we want to use that. Okay? So we want to measure the gamma L of the lobe. We don't want to use directional couplers because they make certain it's non-directional. And we want a small size, and we don't want it to impact the signal. We don't want to have loss. So it's going to work with like 30 dB couple or thereabouts. So this is our first version. Our first try was very simple. This is my line. I came with 2 sniffers, very closely spaced. These actually don't touch. They're very close. And if we do the math, and we did the math, and we figured out, we're actually able to get measurements that are close to the VNA. So you see here the VNA and the simulation and the measurement with the reflector. You can see them here in a photo. It's not exactly the same as VNA. But do you think for what you're trying to do, this is important? It's not relevant. If you're trying to have a 10 dB, 15 dB match, you're not worried about having that precision of 0.1 dB or 1. So this is good. But the problem with this is that if you're going to do this at the surface, we have biasing, we have other things. So we wanted to do a second iteration. Second iteration, we really leverage LTCC. Remember, this technology has all of its advantages. So this is my line. I come enter the line with VS, but don't touch. Then I go from those VS out with transition and match my transition, and then I can build these things. Okay? So here is a 2 millimeter spacing. This is actually, this is 2 millimeters. I have a 4-port device. The load gets connected here. It's a double stub tuner to just change frequencies. And then I'm sampling waves on 2 sides. And this is actually the setup. And you can see that, well, we have some measurement, but accuracy is really not that good. So when you have a problem like this, it's very tough. We do what everybody else is doing. Now, we throw it to machine learning. Because humans are not sufficiently intelligent to handle that complex problem. We do this. So we can say, okay, this is my interferometer. I train it. I make a machine learning approach. I give it different loads. And for each load, I tell it, I see what I'm sampling. Then, okay, after training, I actually give it a different load and tell it, what did I measure? So you can see now, okay, this is simulation, this is the actual measurement. So we tried all of these loads using the machine learning to determine gamma, not equations to find gamma. Okay. The previous figure we used equations, here we use machine learning, and you can see that we have very good accuracy. So I hope now that I convinced you of the second block. First block, my students. Second block, these 2 millimeter space. Sniffers coupled with a machine learning algorithm. So what's next for us? We have to close the loop. Okay? So this vision is, this control intelligent. We can actually make this an intelligent company, not just be programmable. If we have enough intelligence here, it can sense itself, know what's going on, and set itself for the condition that comes from the fund. And obviously, we can leverage the LTCC to have, the RF components, sensing, the sniffing, the control, the power, distribute those parameters. So that was the first part of the field programmable research that we're doing. And switching gears now to the amplifier. So we're doing different things on the amplifier. First thing is we work at the design level. Circuit level, so we've done some work. We've recently worked on this continuous class GF-1. So class GF is essentially working with input and output harmonic tuning. Okay. And so this is a design. We're using LTCC for minimum loss, okay, in the input and output. So this is an actual device that the PA that was fabricated, and these are the kinds of results that we're able to achieve. Okay. So we're achieving, in the neighborhood of 43, 42 dBm to power, and this is a quite wide band. And you can see in terms of efficiency, depending on efficiency, you can see that this is my drain efficiency. We're flirting with the 80% efficiency at power. Okay. But then when it comes to linearity, if you see this loop, for example, 3.1 gigahertz, I have a little higher efficiency, I have a little worse linearity. It's kind of, can gain on all directions. Okay. But this is actually actual measured stuff. And this is actually quite a good performance as an amplifier. The trouble is, at the nonlinearity, this performance is not enough, and you have to do something about the nonlinearity at some point. So this is actually comparing this to the literature, and really, we are, particularly with drain efficiency, we're very competitive, very good. If you look at efficiency and bandwidth, essentially, I think we're very much one of the best designs that's published. And also, skip over this. And this is actually class GF and class GF -1. It's basically depending what you do at the output harmonics. And we also did the second design, and this is the design of it. So these are actually the measured results of this guy. It's not, we're able to achieve wider bandwidth, a little bit wider bandwidth, but we're not able to get quite the same efficiency. So there's an alternative there. If bandwidth is absolutely necessary, then we have to have that compromise. Another thing we're doing on the because I know time is short, analog predistortion. Okay, so we're actually working on analog predistortion. The reason is when you do very wide band signals, digital predistortion becomes impact because the speeds you need for signal processing to follow very wide bandwidth and the resolution of the A to D and D to A converters become exotic. They become too tough. Okay. So whereas analog is basically just analog. Okay. If you do a chip, and so you can see here this design, we're using cold FET in a balanced architecture. Okay. And we're able to achieve up to 6-7 dB of expansion, okay, between 5 and 6 gigahertz. So these are actually the results. So this is our predistorter. We use this with a commercial PA, and we applied this. We tuned it to linearize this PA. So you can see here what kind of performance you're able to get. So essentially, all this area between the dashed and the blue line is gained. We gained in linearity, and you can see it here. It also translates in efficiency without PA with predistortion. We're actually able to increase efficiency quite a bit for the comparable linearity. So this is something we're doing, and we're working on now this hybrid digital and analog predistortion. Can we go further if we hybridize? Okay. Very quickly, I'll start to go a little faster. So thermoelectric conversion. So the PAs are not efficient still. There is quite a bit of power that's dissipated. Can we recover some of that power into reconvert it into from thermal to electric, and we've done some work. So using this is a principle, the Seebeck effect. There are different materials that have different coefficients, and we were working with this material in particular, and we tried to make this this junction using two different materials that have a Seebeck effect to collect essentially to recycle some power. So unfortunately, the idea is okay, but the materials we don't have enough sufficiently high coefficients because we're not able to generate a lot of energy. So if you look, this is an actual fabricated device. We're using nickel and silver as this because there's to make this junction. And if you put 2 watts of power in, we're harvesting 230 milliwatts. So it's not okay. Not that. Another idea is we said, okay, can we do indirect harvesting? So if we have heat, if we put piezo materials that get stressed with heat, can we convert that? And would that give us a little bit better efficiency? Okay, so this is the modeling. So we do this in this piezo, and it will be subjected to thermal stresses. When it's subjected to thermal stresses, so this is the stress distribution. Okay, if we have input power of this is in watt and this is in milliwatt. So on 100 milliwatt, we're getting 0.14. Okay. So if you go all the way to 3 watt or 2 watt, we're harvesting 60. So this was a research curiosity kind of thing, and the idea is we had the technology to try it with LTCC, so we tried it, but didn't pan out as a good way. But still, there might be a way to do some hybrid structures that can actually help us get a little bit more out of this. switching gears to another. So this I talked a little bit about this size and loss reduction in millimeter waves. So this is if we try to do a waveguide in LTCC. Okay? So if you look at the air-filled rectangular waveguide, its loss would be this in the millimeter wave, 55 to 65 gigahertz. This is what the best waveguides are. Okay? This, if we do a SIW, for those people familiar with substrate integrated waveguide, essentially you come to the substrate, you do metallization top and bottom, and you put cylindrical vias to emulate a waveguide. That's the convention. If instead of doing cylindrical vias, we do rectangular vias, so it's closer to a rectangular waveguide. We go down. If you take your waveguide and you fill it with the same material, so rectangular vias is very close to the rectangular waveguide. The other way is if we empty the LTCC integrated waveguide, we get it. And so this we've done this in the lab. Okay, so we wanted to make a LTCC integrated waveguide. We're doing vias like this. And this is something that we fabricated. To measure, we need to design transitions, so the CPW to SIW transition. And you're looking at measured and simulated results between 55 to 67 gigahertz. So we're not bad. Obviously, there are some issues whenever you make fabrications. There's probably some issue with the shrinkage of this LTCC that gave us that. Vertical stuff. Okay. So when you go to millimeter waves, it turns out that if you stack enough layers, you can actually make waveguides vertically instead of horizontal. Okay. And so this is how we make a rectangular waveguide vertical. So we take n layers. In each layer we do this, and we stack them together, and we have a rectangular waveguide. So this we are able to get a rectangular waveguide behavior, but vertical. And we've then done some modeling and so on. But once we've done that, then we've done these transitions. So vertical LTCC integrated waveguide, CPW. So we designed the transitions so that we can measure these things. So we have very good transitions. So you can see that from 54 out to 66, we're better than 10 dB. Transition, and we had different ones made and all made. So next, what we've done, we said, okay, if we want to make circuit in 3D, so we need this waveguide, then we need the components. We need the corner, we need bands, T's, and so on to make 3D components. So we've done this, okay, and we've actually done this T structure to make dividers. Okay. So we did our first design was actually, I don't know if this picture is clear. So this is actually a power divider. Okay. And this is an X-ray view of this power divider that's vertical. I forgot how many layers, it's probably 20, 25 layers. And this is, you're looking at the actual fabricated, this is the top surface. So this is a device that's vertical, and you're looking at the measured and simulated data. Okay. This device, and we have fairly good agreement. This is a coupler. So if you want to make a coupler through holes, for those who do this waveguide couplers and thing, we do the same thing. We try to do the same thing vertical. Okay. So this is my coupler. It's 5.4 millimeter by 2 millimeter. Okay. But it's actually implemented in about 25 layers of this ceramic. Other components. Okay, so this is actually a ninth order V-band filter. So if you look at, again, this actually quite remarkable performance. This is a 2.2 millimeter by 3 millimeter device. Okay. It's just a little bit thicker than your conventional substrate. And it's giving me, measurement and simulation are virtually on top of each other, okay, at 60 gigahertz. So this stuff is thanks to this technology. It's low loss, it's high integration. We're able to do this kind of thing. Switching gears to system and package. So I talked a little bit some of these challenges, but I'm just gonna skip over. So this is a design that we did for a high-speed integration of optical electronic chip. This is for the company that does this stuff in Canada that does this terabit per second modems. And when you do terabit per second modems, you have huge bandwidth, and every transition becomes critical. So so you have the silicon photonic chip that does the optical communication, and you have the CMOS chip that does the electronic interface. And how do you put them connected together with such high bandwidth? So this is it, became critical. So this, we've developed a way to do it in LTCC. We had this package done, and we were able to get this, almost from 20 to 50 gigahertz transitions that allow us to interconnect the silicon photonic chip to the CMOS chip over such a wide band. Okay. This is actually a figure, an actual picture of the actual prototype. So this work was done in collaboration with the company and the university, because they do a lot of work up to silicon photonics. Okay. If you want to do low frequency stuff, so this is, this was back from, I think, 2016. Well, so this is the cover of the IEEE transactional components and packaging, and they were featuring our designs of very compact dual frequency filters in LTCC. So what you're seeing here, you're seeing toroidal inductors, and in the center there are capacitors made in this multi-layer technology. If we want to do some more integrated stuff, so we can do, for example, we've done this multiplexers. Okay? So we actually, what we do, okay, let's say this is my input signal, and I have a directional filter, essentially two couplers interconnected, okay, in LTCC. And so now I can have a wideband signal. I can sample this one channel here, another channel there. I can do multi-channels. Okay? And this is an actual device. This is a second order, okay, filter. So we have one channel here, 3, 4, and 5. We have 3 channels, okay, of this. And this is looking at a cross section of how this is made in LTCC. So we're able actually to do a wide variety of components with this, so multiplexers and so on. And this part is what we talked about DRAs early on. Dielectric resonators are usually made out of ceramic, high-K ceramic. So in this case, we actually worked with this too. So we developed not a high-K, but using the same ferro A6M, we make the substrate, we make the feed line, and then we put a slot, and then we put dielectric resonators. All in one fabrication, one ceramic. If you try to do this in conventional technology, you will have a lot of issues with alignment and so on and so forth. So we actually did this, and we actually iterated. So this is our actual final design. We added some gears and grounding. So this dielectric resonator basically sits on top of in a groove in the LTCC. So this is fabricated with the same materials, same technology, no alignment issues whatsoever, and this was done for 28, 29 gigahertz. So you can see that the single element is able to achieve a good gain over a substantial band. Then what we've done is essentially design an array out of it. So this is essentially a 16 element 4x4 array with a corporate feed, okay, network from underneath. you're looking at the fabricated device. So this is 25 millimeters, about 1 inch, and these are 16 parts. The feed network is on the other side, and this is simulation and measurement. You have 10 dB match between about 27 and 30 in about it. And in terms of gain, we have around, this is the pattern, this is the normalized gain, so we don't gain, the actual gain is here. So about 16 dB gain with that structure in system 1. We'll do some stuff on this, reconfigurable intelligent surfaces. So we are using this cavity. One thing that I didn't mention, in addition to fluids, we can use actually conductors to fill cavity. So Galveston is actually liquid metal. It's a metal that's liquid at room temperature. So going back to that reconfigurability concept, if you put conductors and take out conductors, you're changing the field, the wave propagation, changing properties. So if we want to do this, for those who are not familiar, this reconfigurable intelligent surfaces is essentially passive structures that are not, they don't have amplifiers or anything, but you can just do this beamforming by multiple reflecting elements. If you control the element and you have an array of them, then you can conceivably do this beam steering. Okay, so this is the idea. So if you put an array, so you can do this fluidic base, you can do connectors, diodes, lamps, so on. But what you want is a structure that's low cost, no energy consumption, that will allow us to do beamforming. If you have that beamforming, then you have this ability to use the spectrum more efficiently, to improve coverage and all of these other things. So this is one idea. So if you look at this component, if it is empty, it actually has full reflection. If it is filled, it becomes absorbed. So this is one way of using it. But we're also looking at ways of coupling MEMS to that. So my last probably slide is, so this is, I mentioned that we can do this duplexing, high isolation duplexers. Okay? So this is a structure, this is the one that I mentioned is patented and licensed. What we do is essentially take a duplexer, but make 2 copies of it. And when we make these 2 copies, the leakage between transmitter and the receiver, I have 2 copies of the leakage. I just managed with using hybrid couplers, no active component. I have 2 copies of the leakage. I make them out of phase with each other at the receiver. So if you look, this is the single duplexer isolation. This is this new duplexer. And no electronics, no control, nothing. Okay. So if you have a spectrum crunch, one of the problems is because of the lack of isolation, you are obliged to space out. Okay. You space out your frequencies, your TX and RX. Then it costs you more spectrum. But if you have good isolation, then you can bring them a little bit closer. Ideally, you would like to be able to do true full duplex, same transmit and this. But that's a lot tougher problem to solve. Okay. So I think I've run out over an hour. I just want to conclude by saying that LTCC technology, I think, is well suited for many applications. It's a good technology, including microwave and millimeter wave. The inherent 3D capabilities, they really open thing. Probably you wouldn't be able to do if you are restricted to conventional fabrication technology. It has more promise for millimeter waves. It's fast 5G passive and function factor integrated antennas as I showed you. So I believe that this is a good platform for us for 5G plus to provide this more advanced components, be it field programmable or maybe for this surfaces and so on. And with that, I would like to thank you all for attending, and any questions I'll be happy to answer.
Thanks for this great presentation. So I'm wondering, we have like a prototype for this. This risk example you show is like, I mean, what's the technical features, like what frequency, how many elements? Is it also available for us for having?
So risk, you're quite familiar that this basically the idea started as a concept. Somebody published a paper in 2015, says, if we use risk, we're going to solve it. But risk is low cost. But the reality is there's no such a thing yet. What we're working on, we don't have a full prototype. We're doing stuff that I didn't share because it's still, under development. I think what we have this building approach. So we need the reconfigurable set. That we already have a process to make maps. We have a process to make fluidics. Obviously, we can use diodes like everybody else does. But I think to me, the main problem that has to be solved, if this technology is going to really become viable, now it really has to be low cost and low power consumption. So we're working on ways to actually reduce the component count, reduce the wiring, reduce the complexity, so on. So it's very much still an area. I know that there are a few companies. I know Turkcell is using some things here. I don't know what is being done here. But in our group, we're in the early stages. If we're going to do something in terms of fine prototype, we should do it because the LTCC process that we have, the standard size that we can have, is about 10 by 7, 10 centimeters. So if we want to go low frequency, we have to find a lot of them, and it becomes costly. So we probably focus on range. And we are probably going to use a higher cable. So when you have a high direction constant, the same physical size, if it becomes electrically larger, so we have more capacity. Same size. So that's where we have early simulations. We have initial results that are putting us on a path of reduced components, so reduced cost. But those are not conclusive yet, and as soon as that is fixed, we'll probably publish that. But we're actively working on this.
Okay, so actually we are working with Turkcell as well for risk-related research. Right now, the TÜBİTAK is actually there is another research institute, Marmara Research Institute. There's RF laboratory there, so we are working sub-6 risk, but we are using diode approach. For millimeter wave, when we say like for larger risk, it's highly expensive. Like for one diode is like approximately like $2, so you need like maybe $1,000. So it becomes like really expensive. And this technology we heard about it, like maybe cheaper way to produce the risk. I mean, if there is like opportunity, maybe we can collaborate with you. So okay.
So I think it's one of the objectives for me coming to Turkey was to establish connections. So I showed you the technology that we have in the lab. I think and leverage that. And the partnership we have with the company Vibrant is strong. We have this ability to try out materials. That's often, honestly, not everybody has that chance. So it's always the tools that we use to a large extent impact the research and the ideas we try. So if you don't have certain tools, your observable space, if you will, So I like the fact that we can do regular PCB, no problem. Yes. Using the ceramic approach. We can do five types together and so on. So that's not an issue. But I think from a research standpoint, from proof of concept standpoint, we want to start with a retargeted, limited application. And the goal is really to go to zero entries. Is it feasible? I think so, but not if the RF people try to do it alone and the communication people try to do it. It will not happen. It would have to be a co-design solution. So the reason I'm an RF person, but I'm with Professor Arsenal's group who's communications. And it's really very enriching to me to make this effort to understand and to learn how they think, how they look at things, and take that to enrich. And sometimes I actually give the feedback, saying, you guys are, sometimes they ask very, very dumb questions. Why do you guys do it like this? If I'm IPA, if I'm an amplifier with Bluetooth signal, why don't you do this? And that doesn't come to them because they're kind of two sides. So there is a lot of potential gain achieved in this collaboration. Sharing information. So this presentation I gave about the RF field profitability, to me is really it's a question. What if the RF is fully programmed? Do you do communication the same way? Oh, I hope somebody will say we do extreme power integrity. We'll just take a whole chunk, put everybody in, and everybody's just changing a way. Maybe it will be good enough with a couple of gigahertz of that. So
I'll send follow-up email so that you can.
Absolutely. So let me just go back to slide 1 so that if you want to have my email address, I believe is in the first slide for contact information. Okay. Any other questions? Yes.
You saw the example of the vertical waveguides, which consists of 24 layers, right?
I don't remember the exact number.
Yeah, okay. Can you tell me the thickness of each layer, or what's the limit of the thickness of the ceramic layers?
Great question. So the standard thicknesses that we receive from the supplier, they're typically 3 thicknesses. We have 2 mils, 250 microns, 5 mils, 125, and 10 mils, 250 microns. So when you're building, depending what you're trying to do. If I want to do a coupler, I use 2 mils. And I can do 3 dB couplers relatively easy. If I want to make a substrate and I need thickness, okay, then I'm stacking 10 mils. Okay. If somewhere in between, and you're not obliged to do one or the other exclusive, you can mix them. You can have 1 layer of 2 here, 5, 10, whatever mix. Okay. And experimentally, we can do 1 mil layers, and we can do dielectric paste. So I could just paint a little bit of dielectric. I could do a few microns. Experiment. But again, it goes to this idea of, research and trying things out. But if you want to do repeatable stuff and so on, it's another story. But that's the
The supply is in the form of laminates.
Yeah, they're laminates. They come in this. Well, you know, in our lab we need laminates. Usually, you can get the powder, okay, and you can do the tape casting. So we can actually cast the tape set, but we don't have that equipment. That we prefer to get it laminated from the supply. These guys actually make the materials that if you use ceramic capacitors, these are, you know, they're using these types of ceramic, and they use them in multi-layer MLCC, multi-layer ceramic capacitor. Multi-layer ceramic capacitor, they're using this material, except they use it in thinner, and you have this high Q capacitor because ceramic capacitor is with similar materials, and the higher K materials. It's okay. When I came all the way from Mediport, from Cavagel. So if you have a question, please don't hesitate.
Are you right now in Mediport or like this?
My stay, I came for 6 months, started in February, and I'm leaving on the 31st. Okay, but I've already had, I have a started collaboration with Subsystems around some of these ideas around communication, integrating RF and components, doing some work on ambient IoT devices, how to use those. So it's always this, the communication people always feed you ideas, but there always comes some question mark, how do you make it best? How do you do ambient IoT communication? How do you manage interference? How do you power things? And so in a system level, everything is nice. This is a black box, or this is a line, and so on. In physics, how do you make it? How do you manage isolation, installation? And so it's interesting because the applications are lots of applications. Don't run out of challenges. Just we need to always be on the lookout for. Yes.
My question is about the future. You show us a benefit. As I remember, one of them was 9045, and one of them was about Canada, right?
Yeah, the spectrum.
Yeah, about spectrum. And when I read the Ericsson Model's report, it says that in every 3 or 4 years, the demand of bandwidth is increasing double. So in the future, we will use terahertz. And do you think the RF technology will support that, or are we gonna find any other technologies?
I should think that how to answer it. So so this goes to a topic that's very close to my heart. It's how do you teach electrical engineering? The electromagnetics, the spectrum is the same. The equations are the same, they're unique. But how do you deal with them? You do Kirchhoff's law, you do transmission line, you do waveguide, you do ray optics, you do geometrical optics. How do you model, how do you do this? So when you go to terahertz, is it RF or is it what is it? Fundamentally, it's the same equation. So the RF techniques would apply. So, but it's such a high frequency, but the sizes are electrically huge. So you need to somehow find this right way of adjusting your microwave, millimeter wave RF techniques to work in the terahertz. Because terahertz is not quite optics yet, but not millimeter waves. A little bit further down. So as far as work threads, as far as the tools, how we design, and so on, yeah, it comes with some challenges. But probably one of the biggest challenges is always this energy generation. How do you amplify it? And the other problem is range. How far can you go? It's good for very near field, up very high temperature. No. Already at 5G millimeter waves, you don't find lots of operators, planning to deploy this. Actually, in the US, very few operators, they deploy in very, very limited areas. Involved means concept areas, and capacity. All that, it's the propagation, the cost of the infrastructure, it's not there. So going to terahertz, my early slide is, I think my personal opinion is step back. I think we haven't exhausted the way we do lower frequencies, certainly not. And I think a large part is because if you look at what communications do now, communication is about electromagnetic. No longer about as much about things. It's about people, it's about attendance, it's about propagation. It's about these concepts. If you look at what I'm trying to do, it's about this field programmability of RF. So the main challenge is really in the RF electromagnetics arena, which is inhibiting better use of the spectrum from communication. So if we're able to do that, get smarter technologies and so on, maybe we will not need to go there to make better use of the existing spectrum. Because if you take any spectrum, and it's not used fully all the time. It's not all the time fully used, etc. And including the non-communication bands. We have lots of bands that are out there, that are reserved and so on. So if everybody could cooperate better and do this, we should better resource sharing, cognitive radio and techniques like that. Anyways, I hope at least I gave you some elements of. Okay. The last question. Any question? People on YouTube ask questions, or they can. They're done. All right. If no more questions, thank you again for coming. And do you have my coordinates? Anytime you have any question or anything, please feel free to reach out. Thank you. For those who want to take a look at the ceramics, the LTCC,